So hey guys, welcome back to Spider-Man's lab, and today we are going to study delta to star conversion and the chapter DC circuits in the subject basic electrical engineering. This is your host Spider-Man 610. So let's start. So here we've got a star configuration which we have to convert into this. We've got a delta configuration which we have to convert into a star configuration. So let's see. So here are basically three connections, but we are looking at this independent part of the circuit. So here currently nothing is connected in the circuit. Now we take a multimeter and put it onto the resistance value, and we put it across B and C and check the resistance value between that. So what will happen? The circuit would be like. So this is A, but since there's nothing connected at A, so this part can be ignored completely. And here, since it takes a lot of space, so we have named all the resistance A, then B, then C. So RBC is equal to A times B plus C divided by A plus B plus C, which is simply the parallel of this and these combined. Now on the other hand, if we look at this one, then the active resistance between these 2 points would be simply R2 plus R3. So now we equate these two since they both are equal. So R2 plus R3 equals A times B plus C divided by A plus B plus C, which is equal to AB plus AC by A plus B plus C. So similarly, if we do for AB, so RAB, we'd get R1 plus R2 as the resistance here, and R1 plus R2 is equal to, I'm just skipping these steps here. This one would be equal to C times A plus B by A plus B plus C, which would be equal to AC plus BC by A plus B plus C, and the last combination we get here is AC, which will be equal to R1 plus R3. Now R1 plus R3 would be the remaining one, B times A plus C, A plus B plus C, which would be equal to AB plus BC plus C. So this would be our equation 1, this would be our equation 2, and this would be our equation 3. So we can remove this one right here and write it R1 plus R2 equals, sorry, yeah, we can leave it like that. So now adding 1 plus 2 plus 3. So we get R1 plus R2 plus R2 plus R3 plus R1 plus R3, which would be equal to R1 plus R2 AC plus BC plus R2 plus R3 AB plus AC, and R1 plus R3 which would be equal to this value AB plus BC, B plus BC, and since everyone's denominator is the same, so it would be A plus B plus C. So as you can see here, there are two R1, two R2 and two R3. So, and here also we've got two AC, two BC and two AB. So 2 R1 plus R2 plus R3 would be equal to 2 times AB plus BC plus AC divided by plus B plus C. So we cancel the 2, and this term right here, this is equivalent to, sorry, this one, equation 1. So R1 is equal to AB plus BC plus AC divided by A plus B plus C minus equation 1. So that would be equal to AB plus BC plus AC divided by A plus B plus C minus, now we subtract this, AB minus AC upon A plus B plus C. Now note, I have just multiplied the minus 1 inside as well. That's why we've got both minus. So R1. Now since the denominator is same, we can directly do the calculations. AB goes here and AC goes here. So R1 is equal to BC by A plus B plus C. So this, as you can see here, R1 which is equal to B into C upon total. So this into this upon total. So similarly, R2 is so the trick here is that whichever branch you are looking at, that is the multiplication of the adjacent resistance upon the summation of total. So let's look at it with the help of a question. So the question diagram is given differently in a book, but I'm drawing it in a different way to show how question in exam can trick you. So we've got to find the equivalence resistance between A and B. So this is how questions tend to trick us. You might look at that it is a rectangular shape, but it is just a simple Wheatstone bridge attached to 2 ohms resistors on either side. So first step to always solve a question that's tricky is to break the circuit diagram into a sophisticated piece. So let's look at that. So as you can see here, this complicated circuit has been reduced into a simple circuit which we are familiar with. So in this circuit, we can have we can see that there are 2 deltas here. One is this one, 2, 4, 2, 4, and 6, and one is 6, 6, 7. So it is up to you whichever delta you choose. I am going with this one. So let's look at this one and convert it into a star. This is A, this is B, this is C. So as for the trick I told you about, the trick was A is just the multiplication of the adjacent resistance upon the total. So A is equal to 2 times 4 divided by 2 plus 4 plus 6, and that would give us 2 times 4 divided by 2 plus 2 times 4 divided by 2 plus 4 plus 6, and that will give us 0.66667 ohms. Similarly, B is equal to 2 times 6 divided by the total. 2 times 6 divided by the total. Which is 1. And C right here is the multiplication of these two divided by the total. 4 times 6 divided by 2. which would be equal to 2 ohms. Okay. So now we can convert this diagram into a better one. So this is A, this is B. Now notice how there were two deltas right here, but once we converted the first delta into star, the second delta also automatically disappeared. That is the thing. People in the such questions convert both of these into star and then solve it wrongly. So that we must avoid that. And A here, right here, is 0.66667 ohms. This C right here is 2 ohms, 1 ohms. And this one is 7 ohms, this one is 6 ohms. So this does not look good to me, although we can solve from here as well, but I prefer going it in a rectangular fashion, doing it in a rectangular fashion. So we club this and that is like this and we go. So this is 2.66667 ohms and we've clubbed this, which is 8 ohms, and here also 8 ohms, and this one is 2 ohms. So since we know that if two same resistance are in parallel, then we just divide it by 2. So which would be 2.66667 ohms, 4 ohms, and here 2 ohms. So now you can see this circuit has been reduced into such a linear circuit, and now we can directly calculate it using 2 R A B is equal to 66667 plus 4 2, which is equal to 8.66667 ohms. So that is it. Star to delta conversation. Thank you guys.